So now let's look at the decomposition based approaches. Okay. So here the idea is more or less same. The idea is that we either construct a matrix or a tensor, right, and then we decompose it, right. The matrix decomposition, matrix factorization, we all know how to do this. So we decompose it, and basically the idea is that we try to generate a summary for every timestamp, and we look at the differences between two summaries. So a method, the method first extracts the principal eigenvector the same way from the adjacency matrix of the graph. In the previous case, we extracted the principal eigenvector from the from the similarity matrix, right, the Pearson correlation matrix that we generated, right. But here we extract the principal eigenvector from an adjacency matrix. We call it as the activity vector. Then we apply SVD on the matrix that consists of the past activity vectors in a time window W, and then the similarity between the current and the typical activity vectors in compute is computed as the cosine angle. Now this is very similar to the one that we discussed earlier. Okay. So let's now spend some time on another type of algorithm which detects anomalous entities based on the community structure. Okay. So right, dynamic graphs, community based methods. So it monitor graph communities or clusters over time and reports an event when there is a structural or contextual change in any of them, right. It looks at the changes in two consecutive snapshots of the graph or all the snapshots of the graph, right. Detect communities and outliers simultaneously. Let's look at one such algorithm, and let's focus on this algorithm. This is called evolutionary community outlier algorithm. It is also known as EC outliers. This was published in SIGKDD 2012. Okay. So let's look at the intuition. So most of the objects within a community follow similar evolution trends, and their average defines the evolution trend of a community. Okay. Let's assume that we have three communities at timestamp t1, okay, and you focus on let's say this community, okay, and you see how this community behaves, how nodes move from this to this to this, right. So generally, if this community is a normal community, its constituent nodes also behave similarly throughout the timestamps, right. Say this node will move to this node. If other nodes also behave similarly, they would also move to this community. Okay. So, but if there is any change in the evolutionary behavior of certain objects, then we say that this community is basically an outlier community. So evolutionary behavior of certain objects is quite different from the average evolutionary behavior of its community, right, and the goal is to detect such anomalous objects, right, given a pair of snapshots. So this is timestamp t1, timestamp t2, we look at every pair and we measure this abnormality. Let's take an example. Let's take a few examples. So let's assume that a stockbroker, right, who suddenly changes his portfolio and starts investing in another sector against his historical investments, even when other similar stockbrokers continue to invest in the same old sector. This is definitely an outlier behavior. Example 2. So let's take the research career of say Professor Soumen Chakrabarty, who is currently a professor of computer science in IIT Bombay. So, till 1997, 1998, he used to publish papers in parallel systems, parallel architecture, parallel systems, mostly systems conferences. But around 98, 99, he started publishing papers in data and information systems like conferences, WWW, KDD, WSDM, etc. So, this is definitely an anomalous behavior, because the rest of his neighbors of the same community, they still kept on publishing papers in system conferences, whereas he suddenly changed changed his research area and started publishing papers in other areas, right. So, definitely this is a community based outlier with respect to that community. In 2010, there are 13 papers in a CIKM conference. CIKM is a data mining conference, and these 13 papers were about personalization, right, where none of the other IR conferences like WWW, WSDM, SIG-IR, they focused on so much on personalization. So, if you look at data mining conferences, you have CIKM as one node, KDD another node, WWW another node, WSDM another node, and most of these conferences do not focus on personalization, whereas CIKM started focusing on personalization from 2010, right. So, definitely with respect to this community, CIKM is an outlier, okay. So, these are called community based outliers in a dynamic graph, okay. So, let us look at the architecture now. So, we have a snapshot of graphs, right, x1, x2, x3, .. right. So, you can think of this as different snapshots, right, and then you focus on a pair of snapshots, right. So, this is one snapshot, this is another snapshot, okay, and you focus on a pair of snapshots, say x1 and x2, right. P is a matrix corresponding to x1 snapshot, where each entry Pij indicates the probability of node I belonging to community J, right. So, this is a n cross K1 matrix. N is the number of nodes, K1 is the number of communities in X1, okay. Similarly, we have another matrix Q, this is n cross K2 matrix. K2 is the number of communities in at timestamp K2 X2, right. You see here, if this is X1, there are 3 communities, K1 is 3, if this is X2, then you have 2 communities, right, and Pij indicates the belongingness of node I to community J. How do you measure it? You can measure it in many ways. For example, you can look at the number of edges of node I in community J, right, and so on. So, right, we also make sure that each row, entries of each row, sum of entries of each row should be 1, right. Pij. So, the total belongingness of a node to different communities is 1, and you have partial belongingness to different communities, right. Similarly, you have this one Qij 1 to K2 is 1, okay. and this Q1, Q2, this P and Q you can easily measure from the algorithm, right. Let us look at some other notations. X1, X2 are snapshots, K1, K2 are number of communities in X1, X2 respectively. Total number of nodes is fixed n. P and Q are the belongingness matrices. This I already mentioned, the sum of row should be 1. Then we introduce another matrix S. So, S is the correspondence matrix, right, and this is K1 cross K2, number of communities in X1 and number of communities in X2, right. It basically says that, say there are two nodes here, some of the nodes move to this community, remaining nodes move to this community, right. So, this S is an association matrix between K1 communities and K2 communities, okay. And this association matrix or correspondence matrix is something that we learn, okay. Similarly, we have another matrix A which is n cross K2 matrix. This is called outlier matrix, outlierness scores, where Aij indicates the propensity or the extent of outlierness of node I to community J, okay. And what is the objective? So, an object community pair, okay, ICI for example, is an outlier if the change in POI to QOJ, right, O is the object, from ith community it is moving to jth community in the next timestamp, is quite different from the average change from community Xi to community Xj, and our task would be to identify such outliers, okay. So, now let us look at the algorithm, right. So, it is called an integrated framework, and what is the task here? The task is to estimate S, right, and A, right. So, S is the correspondence matrix and A is the outlierness matrix that we estimate, and what are given to us? We have Q, we have P, right. Now, so think about it. So, at X1 you have this P matrix, you have some correspondence and you get X2 and Q. So, ideally, and this correspondence is S. So, ideally P times S should be same as Q, right. So, this should be the ideal scenario. So, Q minus P times S would be the error, right. So, look at here. So, this is the function, we are minimizing the error, right, between Q and P times S, right, we are minimizing this. And the problem here is that if we minimize, right, it would basically be biased towards outlier entities, right. So, we need to add some quantity which reduces the bias of overall algorithms towards outlier entity. So, for that what we incorporate a log loss, not a log loss as such, but a log weight, right. This is 1 by A. So, let us look at this one. Okay. So, what is A? AOJ is the outlier score of node I to community J, okay, and this is the error. So, higher this outlier score, this would be lower. So, this is basically a weighted sum, this would contribute less towards this error. So, the nodes which are outliers, those will contribute less towards this sum, right, and instead of taking direct weight, we take the log weight, right. Again Q is known, P is known, S is unknown and A is unknown, right. So, we minimize this objective function with respect to S and A. And what are the constraints? So, in the correspondence matrix S, the entries should be non-zero, right. 0 is okay, but it should not be negative, right. It should not be negative. It is 0 or greater than 0, not non-zero, 0 or greater than 0, but it should not be negative, right, for all pairs of K1 and K2 communities. For a given I, the sum should be 1, right. So, if we think of S K1 cross K2, right, each row the sum should be 1, right. The entry in the outlierness matrix, each entry should be positive, 0 or positive, should not be negative, and this is very important. The sum of all the entries of this A matrix, which is n cross K2, the sum of all entries should be less than mu. What is mu? Mu is an user defined constant, right. So, what I am saying is that it should not happen that you arbitrarily say that all the entities are outlier. You can say that. If you do not incorporate this constraint, what would happen is that if I say everyone, all the entries as outliers, right. So, all the entries would be outlier, therefore, the contribution should be less for all the entries, and this should mean the overall objective function should be minimum, right. So, we say that this should not happen, the total sum should be less than equals to mu, okay. So, this is the objective function and these are the constant. So, this is a constant objective function, constant optimization function, right. And how do we solve this problem? We see that there is equality and inequality constants, right. How do you solve this? We use it using, we basically solve this using normal Lagrange multiplier. So, those who do not know what is Lagrange multiplier, right, please go back and check. If you are familiar with SVM, support vector machine, you should definitely know what is Lagrange multiplier, but those who do not know, go back and check what is Lagrange multiplier. Lagrange multiplier is a way to move all the constant, all these constants to the objective function to make a single objective function to reduce the number of constants, right. So, we see here that that this one, right, has been moved to the objective function here, right, and the last one has also been moved to the objective function. So, this was the old objective function, now these are two other constants that have been added to the objective function, right. So, we now want to minimize this. How do we minimize it? we can minimize it with respect to SNA, right, and simply we can use gradient descent type algorithms, minimization, so gradient descent. So we take the partial derivative of this with respect to S, separately with respect to A, right. So this is the updation rule for A. If we take the partial derivative, you see that this would be the updation rule for A, this would be the updation rule for S, right. So let us look at the algorithm now, the entire algorithm. So we start off by assigning mu as 1, right, by assigning all the entities of S as 1 by K2, because K2 is the maximum, I mean K2 is the sum of all the entries of S to of S, right. We initialize A by 1 by n K2. n K2 is the sum of entries of all the sum of entries of A, right. We assign it, this is the initialization. Then we update A and S based on these and these equations, right, and we keep on doing this thing until and unless we converge, right. There is no change of S matrix and A matrix, and then we update mu, right. How do we update mu? Mu is now the fraction of the actual error that is still there, right. You see here Q minus P times S, this is the error, this is the sum square error, and this is normalized by the maximum number present in Q. So this is the normalized error. Now this is our mu. I repeat the same process again, right. So at the end of the day, what I will have? I will have A and I will have S, right. A is the outlierness matrix which we actually need, right. So remember, Aij or say Aoj indicates the outlierness score of object O with respect to community J. Now if this is less than mu, right, or say not exactly mu, if it is less than say certain threshold theta that you define, right, or say greater than, because this is outlierness score, if the outlierness score is greater than theta, for example, then you say that object O is outlier with respect to community J. Okay. So this is about EC outliers. You can read this beautiful paper. This is a very interesting paper published in KDD, and we have essentially exhausted. We have discussed, you know, different types of algorithms for outlier detection. We have mostly exhausted the taxonomy that we started with, right. So this brings us to the end of this chapter. So what we have learned so far? We have learned how to define an outlier. Outlier is an ill-defined problem, right. Depending on certain application, we define outliers. Then we looked at static graph and different types of algorithms for static graph: feature based, non-feature based, community based. We look at dynamic graph, feature based, decomposition based, community based, and so on, right. And then we have seen how we can we use outliers, outlier detection methods for different applications, so fraud detection, cybercrime, right, anomaly detection, outlier, fake news detection, fake account detection, credit card fraud detection, and so on and so forth. Okay. So this is the end of this chapter. So we will, in the next chapter, we will discuss, we'll start discussing on graph representation learning. We will first start with some basics of neural networks, deep learning and neural networks, and then we move to the graph representation learning chapters. Okay, thank you.